Have you thought of how to filter the data coming from an analog sensor? Why do you even want to filter that data? Should you use arithmetic mean or median? Why can't you just grab a sample from Arduino analogRead and be done with it? Those are the questions I had on my mind. After playing with the data I got from my infrared and ultrasonic sensors, the answers became more obvious. In this post, I'll describe 1. Problem with sensor measurements, 2. Way to auto-trigger analog data collection, 3. Median and mean filter application, and 4. Analysis of sample data. I also touch on why my adventure in using ROS on Arduino is put on hold. In the following snapshot, the ladder-like trace shows a signal from sharp 10 to 80 cm infrared sensor. I was waving my hand in front of it. As the trace shows, the sensor spends about 40 milliseconds to take a measurement. The datasheet for the sensor specifies 38.3 plus or minus 9.6 milliseconds. If my code reads analog value from the sensor once every 50 milliseconds, the reading may come from one of the spikes. So when that value is converted into a distance, the distance representation will not be accurate. As is the case with the first spike in the image, the sample will represent the distance from 2 measurements ago, which is bad. A common approach to improve the accuracy is to take multiple measurements and compute the average. Later I'll show you the comparison between all three when measuring the distance to a fixed point. To read an analog value, one can use Arduino's analogRead function. When calling it from a main loop, the CPU is tied up while collecting the samples necessary to compute the average. This may pose a problem because other important tasks are put on hold while this read and wait cycle executes. A better approach is to collect the samples in ADC completion interrupt, which ADC calls when it completes converting voltage level to a digital value. ADC can operate in free running mode, which is okay if I have a single analog sensor. With multiple sensors, the timing of reading the data from different sensors can be challenging to code properly. Therefore, I chose to trigger the ADC using a timer. Since IR distance measurement takes 50 milliseconds, and I want to average over 5 samples, the timer interrupt routine is configured to initiate ADC conversion every 10 milliseconds. At this point, I'm set up with a single analog sensor. But when I add more in the future, the function below will instruct ADC to sample from all configured sensors in turn. Every 50 milliseconds, the code in the main loop will compute the average and send the data out for analysis. In the example above, Arduino sends messages using serial print function. In my previous post, I showed how to use ROS to publish Hello World messages from the Arduino. My plan was to use ROS in this example as well. The plan hit a snag. First, the idea was to publish an array of sensor values. It seemed like a simple task. But to create an array is anything but simple. The code didn't work at first go. While waiting for ROS message board to come out of maintenance, I had time to take a look at the design of ROS 2. That changed my plans of using ROS on Arduino entirely. In ROS 2, the messaging will be replaced with the data distribution service. As far as I know, there is no DDS software for AVR hardware. From my experience, DDS is quite rich in features and provides everything one could ever want from a middleware. For more capable hardware, DDS is awesome, unless I have to pay an arm and a leg for those features. Another change ROS 2 plans to make is to move from Catkin build system to something called Amend. With all of that, more time investment in ROS 1 is not as appealing. Okay, let's get back. Filtering code is straightforward. To compute the median, sensor samples are sorted first. Then, the middle value is read from the sorted array. To compare the data between single value, median and mean, I modify the code for each scenario and print the data separately. All three could also be computed and output at the same time. Once a Python script running on my desktop computer received and stored the data in a CSV file, I load the data into pandas for analysis. In the first case, the code sampled one value every 50 milliseconds and printed that value for the total of 375. In the second case, the code sampled one value every 10 milliseconds, calculated arithmetic mean after collecting 5 samples, and printed that mean to the total of 398. In the third case, the code sampled one value every 10 milliseconds, calculated a median after collecting 5 samples, and printed that median to the total of 317 values. Each value represents a distance from the sensor to a fixed object on ADC scale. The results show that in each case the median value is 132, which is the expected value. Values are spread the least in case of the median field. Its mean is also closer to the median. A density plot shows the situation a little better. The median filter shows the most frequent occurrence of the expected value. Single sample and mean filters show bigger variation between the values. Given the results, the median filter is a winner. Therefore, I shall use it moving forward.